Hello. So in today's video, what we are going to discuss is the second TDS equation. In my previous video, I have discussed the derivation of the first TDS equation as well as its application. So in this video, I'm going to talk about how to reach to the second TDS equation, that is the derivation of the equation, and few of its example. So let's get started. In the previous video, I talked about the entropy of a pure substance can be represented by a function of two variables out of these three at one time. Like we took the different cases, like S is could be taken as the function of Vt, S could be taken as function of Pt, and S could be taken as function of Pv. So we took this one in the last video and we derived the first TDS equation. And we will consider this function today, this form of the entropy today, and we'll see that it leads us to the second TDS equation. And similarly, this one lead to the third TDS equation that we'll consider probably in the next video. Okay, so let's move on and to find out the second TDS equation. All right, so since entropy of the substance we are taking as a function of P and T, so I can write down my ds as del S over del P at constant T dP plus del S over del T at constant P dt. All right, that's, let's say, number one, number two equation. And now using the Maxwell's thermodynamic relation, which are very interesting and important relations in thermodynamics, I can write down using the Maxwell's relation that del S over del P at constant T is actually equal to negative of del V by del T at constant P. Let's say this question number three. So I can substitute 3 in 2. I find the following: ds is equal to minus of del v by del t at constant p dp plus del s over del t at constant p dt. Now, let me call this equation 4. What I'm going to do is I'm going to multiply the equation 4 by temperature T. So multiply 4 by T. So when I do so, I get GDS is equal to minus T del V over del T at constant P dP plus T del S over del T at constant P dt. Okay. All right. So now I can see that this thing here is nothing but the heat capacity at constant pressure. So from second law of thermodynamics, we know that dq is Tds, and dq is also equal to, if I represent the mass of my pure substance in moles, mu Cp dt, Tds. Okay, so that's equal to Cp. If I write down this, Cp is the small cp, right? The small cp means this is a molar heat capacity. Heat capacity of corresponding to 1 mole of substance. Now, when you multiply it by the number of moles, it becomes the heat capacity. This Cp is this is a specific heat. Yeah, specific heat capacity. Okay. This is here is the heat capacity, which is equal to mu times Cp, which is equal to T times del S over del T at constant P. So that's equation 6. So I can actually substitute the 6 into 5. So from 5 and 6, I see that TdS is equal to minus T del V by del T at constant P dP plus T times del C by del S by del T at P is nothing but Cp. So I will put that Cp over here and dt. That's equation 7. And in fact, this equation 7 is known as second TDS equation. So we have reached to the second TDS equation. This is nothing but the second TDS equation. Second TDS equation. Okay, so now we'll come to the very interesting application of this, right? So far we have talked about the derivation part. Now we'll come to the application part. So It has very important application, especially in case of two very particular kind of processes. Number one is the reversible isothermal change of pressure. It's called reversible isothermal change of pressure. So what does it mean? It means that our thermodynamic process is going to be reversible and isothermal. Isothermal means the temperature change doesn't take place, and the pressure will of course change, because this is reversible isothermal change of pressure. We are changing the pressure, keeping the temperature constant. Okay, so in isothermal process, we see the temperature is constant. So we are going to see that how to use the second TDS equation to calculate the amount of heat exchange in such a process. See that temperature is constant in isothermal change, then I can use my second TDS equation and I can write down the TDS is equal to from 7. So from 7, if you see, if my temperature is constant, the second term here, CPDT, is going to be 0, because now the process is isothermal. So CPDT is going to be 0. So what we are left with is the TDS is equal to negative of T del V by del T at constant P dP. Okay, fine. So that's what we got. Now, this is nothing but the heat exchange, right, in this process, dq, because from second law of thermodynamics, dq is equal to TdS, and this is equal to minus T del V by del T at constant P dP. Now I'm going to integrate it to find out the heat involved in the process, and that is minus T, because temperature is constant. So I will keep this temperature outside the integral because it's isothermal process, and when I integrate it over del V by del T at constant P. So that is how we can calculate the heat exchange in the process where the change of pressure is taking place under the isothermal reversible condition. We can further go along and write down the alternate form or the more useful form of this particular result that we have just obtained in terms of so-called um, volume expensivity. Beta is defined as 1 over V del V over del T at constant pressure. Okay, so in that sense, if I number this equation A, so let me put the 9 equation in 8, and I'm going to get the result as from 8 and 9. I'm going to get Q is equal to minus T V um, beta dP. Okay, so that's what I'm going to get. Now, if we take the most of the substances, right, for practical purpose, this V and beta, they don't change appreciably over the huge range of pressure, right, that we apply on solids and liquids. Like for example, if we apply the pressure from 0 atmospheric pressure to some, let's say, 1,000 atmospheric pressures, and V and beta of generally for most of the solids and liquids, they doesn't change very appreciably. So in that sense, they can be treated as a constant for most of the solids and liquids. Okay, so for most of the solids and liquids, V and beta are not very sensitive to pressure change. So what I can do is that I can really take this V and beta outside the integral in that case, and I will be left with this, which is equal to, let's say the pressure is changing from, let's say, P1 to P2, where P2 is greater than P1, and that's the result that I've got. So that is the amount of heat involved in the isothermal reversible process where the change of pressure is taking place. And suppose P2 is greater than P1. So then the heat exchange will be negative if my beta is positive, because V is already positive and T is already positive, right? We are not going to below 0 Kelvin, of course, and we T is positive, V is positive here. So if beta is also positive, then and of course we are working with the condition as P2 is greater than P1. In that case, Q will be heat exchange will be negative. Negative means the heat will flow out of the system. All right. However, if beta is negative, then we are going to get Q to be positive for P2 greater than P1 case, and that means the total heat will be absorbed by the system. Right. So that's the important conclusion that we can draw from this equation and this second TDS equation we can apply. Let's do a small numerical problem based on that, and then we'll quickly go to the other application of the second TDS equation. Suppose I've been given a problem. So this is a numerical problem that if the pressure of 15 centimeter cube of mercury at 27 degrees centigrade is increased reversibly and isothermally from 0 to 1000 atmospheric pressure, then we have to calculate total heat transfer, where few data has been given to us. It has been given that the volume expensivity beta is equal to 1.8 1 to the power minus 4 per Kelvin. That's it. So now let's solve this problem. You see, to solve this problem, we can directly use the result that we have just obtained. Like in this case, the heat absorbed or heat released, both will be we will able to see. Now we can actually see that since beta is uh, positive here, so we are going to get the value of Q to be negative, as I discussed. If Because the pressure is being changed from 0 to 1000 atmospheric pressure, P2 is greater than P1, so we are going to get Q negative, which means total heat will be taken out of this mercury in this process. So let's calculate that. Q is equal to, I got the expression as minus 2V minus TV beta P2 minus P1. So minus T here is 27 degrees centigrade, which means 300 Kelvin. And volume here is 15 centimeter cube. If I take the 15 centimeter cube here, so my volume become 15 to 10 to the power minus 6, okay, meter cube, and beta is 1.81 into 10 to the power minus 4, and this is 1000 atmospheric pressure, which I will have to convert into the Pascal because everything else is in the SI units, which is equal to 1.014 into 10 to the power 5, right? So that's will come out to, so since everything we have taken into the SI units, so it will come out to in terms of Joule. So that's a number, if we calculate, that turns out to be 82.26 Joule. Okay, so that's the answer to this question. That's how we solve this kind of numerical problem based on the second TDS equation. So I hope you have understood it. So now let's go to the another important application of this second TDS equation. Second application for the second TDS equation is in the case of reversible adiabatic change of pressure. So earlier we discussed the reversible isothermal change of pressure. Now we are going to consider the reversible adiabatic change of pressure. Okay, so in adiabatic case, we know that dq, that is the heat exchange, is zero. That is equal to TdS from the second law of thermodynamics. And if we apply the my second TdS equation, which was TdS equal to Cp dt, negative of T del V by del T at P dP. So that's left hand side is going to be zero because the in adiabatic process the heat exchange is zero, and Cp dt minus T of del V by del T at constant P dP, which will give me that Cp dt is equal to T times del V by del T at constant P dP, which is equal to the dt equal to T over Cp del V. Mind you, the Cp here is the heat capacity in the Tds equation. They are not the specific heat, molar specific. They are the heat capacity. Okay, so now this dt, that temperature change that we have calculated due to in this adiabatic change of pressure. In this process, there is some, because heat exchange is anyway zero. So what we can calculate here in this process is the final temperature change that has taken place during this process. So if I wish, I can write down this expression in terms of beta, volume expansivity, that we just discussed, because volume expansivity is something which can be directly measured for a particular substance in the experiments. So if I write down this thing in terms of beta, so this is going to come out beta dp. Okay, now so this is the expression that we get for the temperature change for such kind of uh, processes. For most of the solid and liquid, this increase of pressure, let's say, as I discussed in the last numerical example, from 0 atmosphere to 1000 atmospheric pressure. So for most of the solids and liquids, this much change or increase in pressure does not create a very appreciable change in temperature. So and also the Cp does not change too much in for a huge variation of pressure for most of the solids and liquids. So what we can really infer from this particular equation is, in those conditions, that can be alternative written as delta T is equal to TV beta over Cp delta P. Okay, which is let's say the pressure is changing from P1 to P2, and this can be written as P2 minus P1. Okay, so I can calculate the change in temperature in this reversible adiabatic process by this particular equation. Hmm, equation. Let's do a small problem, numerical problem, as we did in the last case. If the pressure of 20 centimeter cube of mercury at 27 degrees centigrade is increased in a reversible adiabatic process from 0 to 1000 atmospheric pressure. Okay, the temperature change will be, so that's the question. What's the temperature? So we have to find out the temperature change. The given data is that the beta for the mercury is given 1.81 10 to the power minus 4 per Kelvin, and specific volume of mercury is given to us, let's say that is 7.38 into the power minus 5 meter cube per kilogram, and the specific heat was also given to us. It's not heat capacity, this is specific heat, is given as 140 um, joule per kilogram Kelvin. So everything is in SI units. This is given to us. So now we have to simply apply the equation that we just derived, delta T equal to T approximately equal to TV beta over Cp times delta P, right? Which is uh, T here is 27 degrees centigrade, which will convert into Kelvin, become 300. V is C. Now, V is the volume here, and Cp is the heat capacity in this relation that we have derived here. But now in the problem, we have been given a specific volume and the specific heat. So Cp is actually mass times the small Cp, right? So mass of the substance times the specific heat, and the volume upon mass will make it this specific volume, a small v, right? And we have beta as it is, and delta P is of course 1000 minus 0 atmospheric pressure, which will convert into the Pascal by multiplying the equation 1.1 into to the 10 to the power 5. So what we get here is 300 into the specific volume is 7.38 into 10 to the power minus 5. Beta is 1.81 10 to the power minus 4, and this is 1.01 10 to the power 8 divided by the specific heat, which is 140. So if we calculate this, this turns out to be approximately 2.9 Kelvin. Okay, so that's the derivation and the application of the second TDS equation that we have discussed today. Hope you understand and enjoy it very well. Keep learning physics as much as possible. Thank you.